A question that might pop into your head is, why did we have to get the binary interval completely contained in the interval from a to b? You know, we kept going here, subdividing and subdividing, until we got this interval 101, 100 that was completely contained in this interval from a to b. So you might say, why not just stop as soon as we get a number that's contained in that interval? Like in this example, we could, you might say, hey, why not just stop here? We got 0.1011 in base 2 is 0.6875. That's contained in the interval from a to b. And you might say, why not, instead of using this whole thing, 101, 100, encode 210 as just 1011, and then during decoding, you would have, so that was this number right here. You would know 1011, that corresponds to this number. And then you go back over here and you say, during decoding, well, hey, why couldn't we just, at the first step, subdivide in just the same way? And then we see that number is contained in the 2 chunk, so we know that the first symbol must have been a 2. And then we subdivide again, and we see that number is in the 2, 1 chunk, and so we know that the next symbol must have been a 1. And then we subdivide yet again, and we see that the number is in the 210 chunk, and so the third symbol was a 0, and that's the end of file symbol. So therefore, we know that the original message must have been 210. So it seems like you might be able to do that instead. And then, hey, you could have a savings of 2 bits. You would have, had it encoded in a shorter message. So why couldn't we have done that? Well, it turns out that if you were to do that, if you were to stop as soon as you get a number that's contained in the interval and encode using that sequence without going the full distance to get the interval contained, then the resulting code fails to be a uniquely decodable code in a certain sense. So in this video, it's sort of a technical point, but it's a subtle one that I missed on the first go around, and so I'd like to address it up front in case you were wondering. If you don't care, this is not an essential point to understand in order to understand how arithmetic coding works, but if you were wondering about this question, I'd like to address it in this video and explain why you have to get the whole interval to be contained in the interval from a to b in order for your code to be uniquely decodable in a certain sense, and why why you might care about that. So to explain this, first let me explain what I mean by unique decodability and prefix in this context. So before, when we were talking about prefixity and unique decodability of a code, we had some source alphabet X, and then a code on X was just a map from these source symbols to strings, say binary strings. And we said that such a map was a prefix code if no code word was a prefix of another. So we could say if C of x1 is not a prefix of C of x2 when x1 is not equal to x2. That was the definition of a prefix code. And likewise, we defined unique decodability, so we said that this thing is uniquely decodable if the map C star, if C star, the extension of C, is 1-to-1, it's a 1-to-1 map, it's a injection, where C star was this extension, the encoding of a sequence of source symbols is the concatenation of the code words. So that's just a little reminder of what we meant by these before. And now what I mean, it's basically the same thing. It's a special case of this, but now our source alphabet is going to be the set of all the possible messages, the sequences, the message sequences that we're going to consider encoding. So this X star circle is the set of all these finite length sequences, x0 up to xk, where each of the xi's is in our source alphabet and it's non-zero. We're taking 0 to be our end of file symbol. And it's terminated, each of these sequences is terminated by a 0. And we're considering the set of all these possible, over all possible lengths. So it's all of these sequences that are valid with respect to our end of file symbol convention. And so a code on this, it's just the same thing. But let me write it here just to be clear about what I mean. So it's just the same, except we have a new source alphabet. And it happens to be infinite. But that's okay. All of the stuff we did, these definitions all make sense. So it's prefix. And now let me put superscript 1 to distinguish from here. The X subscript 1 was a single source symbol. And let me put superscript 1 to denote one of these whole sequences here. So if this is not a prefix of CX superscript 2, as long as X1 and X2 are different sequences. So this is exactly the same definition, and likewise we would say it's uniquely decodable if this extension is 1-to-1, where now the extension in this case is, it takes a concatenation of these messages. So for example, like, this might be here, this might be like 2, 1, 0, and then 1, 2, 1, 0, and so forth, where 0 is the end of file thing. So this would be like the second thing in the sequence. And then you might have another one, 1, 1, 2, 3, 0, or something, if 3 was in your alphabet. And you encode those in just the same way. You concatenate the encoded messages. So this is what I mean by prefix and uniquely decodable in this context, in the context of arithmetic coding, where we are having sort of, you can think of it as being a different code word associated to each of these possible input sequences. So now that we've got our terminology straight, now let me explain what I meant before, what I was trying to say before, briefly, about the problem with the alternate version of arithmetic coding, where we instead just stop as soon as you get a number that's contained in the interval. So let me call that the number version, the proposed number version of the algorithm. The number version is where that was the alternate thing I described, where you just start, you subdivide until you get a number whose binary, a number, the first number that, the shortest possible binary sequence. What am I saying? Let me say this more clearly. Back up to our example. The number version is the thing I described at the beginning, where instead of going the full distance to get the interval contained in A to B, you stop as soon as you get just a single number, a binary number that's contained in A to B. So, and then you encode with that binary sequence. So let me call that the number version. And let me call the interval version the correct thing, the thing that I have described in the examples so far. So the problem with the number version is that it's not a prefix code. And in fact, in this sense here, in this sense, so this was before, and this is now, in this context. So the number version is not a prefix code in this sense right here. So this is not prefix, and in fact, it's not even uniquely decodable in this sense. I'll explain why in a minute. On the other hand, the interval version is prefix. And so since every prefix code is uniquely decodable, it's also uniquely decodable in this sense. So this is nice, and I'll explain why you ought to care about this. So let's think about this little example right here that I wrote down. So 210 in our original example 1, if we did the number version, this would be encoded as 10, I think it was 1011, right? Let's go back up here. Way back up. Yeah, so it would have been encoded as 1011 because that was the first binary number that was contained in the interval. And of course, so maybe I'll stay here for a sec. So the number version is decodable by exactly the argument I went through at the beginning of the video. It's decodable in the sense that if you only had the sequence 1011, then there would be some unique sequence, source sequence 210 in particular, that would decode to that. But that's not, in general, the situation that we're going to be dealing with. So if you only had this 1011, then you're in perfectly good shape for the number version. But unfortunately, in general, you're not just going to get that. You're going to know that you're just going to get some binary sequence that's going to start with this, and then there's going to be just some other junk back here, some other stuff that's just, this sequence is just going to keep on going. And there's a couple reasons why this usually will be the case. In general, if this is stored on a computer, then you're going to get some pointer or something like that to the start of your sequence, and it's just there's just a bunch of memory, there's just a bunch of data stored in memory, and so there's just this binary sequence, and you don't know a priori how long your sequence is. Now, there's a couple ways to remedy that. One would be to store the length of the sequence, right? So you would have something up here ahead of time, some header that tells you the length. So that it would be like something encoding the number 4 as a header to tell you that the length of your encoded message was 4. And typically, if you're storing something in a file on a computer, then the operating system is going to handle this automatically for you. Or in a lot of programming languages, if you store something as a sequence, this will be handled automatically for you. And that overhead, but this is overhead here. The number of bits that are required to encode the length is some overhead in your total encoded length. Now your total encoded length has to include that header. So this overhead is costing you. So one alternative is just to eat that cost, just say, my encoded length is going to be pretty small on average because, I have a good compression. And so this is going to be roughly the log of the encoded length. The number of bits required to encode the length is going to be roughly the log of the encoded length. So that's not too bad. And I can just suck it up and eat that cost. But that's probably not going to be the most efficient approach in terms of compression, because in a certain sense you're modeling the lengths of the probability of the length of your message being a certain thing in a priori a particular way that doesn't necessarily reflect how long the encoded lengths are actually going to be. So a better approach is to actually use the interval version. And in that case, you don't have this overhead. The code is automatically prefixed, so you can so instead of having this situation, you're going to have this guy is going to be encoded as 10100 in this example 1. And since the code is prefixed, then you just start reading off your bits 101100, and as soon as you get to that last O, then you know that you have read off the first encoded sequence, and or the encoded sequence that was at the beginning of this string, and so you stop and you say this is the end of that encoded sequence. And this is still a very efficient in terms of compression approach. We'll see later on, we'll prove that this actually gets within, on average, 2 bits of the entropy of the source. And that's 2 bits for the whole encoded message. So it's a very good result, very strong result. So on average, your compressed file is going to be within 2 bits of the optimal, of the ideal even. Well, assuming the infinite precision version. And the finite precision version is pretty darn close too. Still within a few bits of the ideal empirically. So the point is that the number version, the reason why it doesn't really work or it's not so desirable, you could use it if you could take this approach and encode the length. That is an option you could take. But so the reason why you have to do that, of course, is that since it's not a prefix code, and maybe I'll explain why it's not prefix in a second. The reason why you have to do that is just because in general your string, your encoded string, is not going to be in isolation given to you just by itself. It's followed by some other stuff. And that other stuff could be, like I mentioned, it could just be other bits in memory that just happen to come after your encoded thing. But it could also be something like, if in this situation where you're, not that one, but this one here, where you're concatenating multiple messages, like in this case, like if, say this one here, maybe this happened to be the encoded string for this 1210, and maybe something later is maybe the rest of this corresponds to this one here. So that's another situation in which this issue could arise. All right. So let me now explain, if you're interested, why it is that the number version is not prefixed. I won't rigorously prove this, but I'll just give you an indication of the reason why. So let's write down that sequence again here. 1011, 0100, 11. This will just, I made up the rest of this. The important thing is that it begins with 1011, which was our proposed encoding of that original sequence 210, this one here. So the reason why it's not prefix is that in the number version of the algorithm, pretty much any binary string is a valid encoded message for some source message. And so as a result, you don't know whether you should first decode one and then the rest of it. So do you do this and then there's something else following? Or maybe you do 1 0. So is it 1? Is the first thing 1? Is it 1 0? Is it 1 0 1? Is it 1 0 1 1? Or maybe something longer? You don't know. And the reason why you don't know is because pretty much any binary sequence is a valid encoding in the number version. So why is that? So let's go back up here to the example. So take like 101, for example. Oh, there we go. Stay. So if we had that long string I wrote below, and we were trying to decode it, and we don't know what the initial, that the initial thing, the correct initial thing was 1011, and we looked at, say, we thought, hey, maybe the first one could be 101. Well, that's actually a valid code. That actually encodes for something valid, right? Because here's 101. Here's 101, and it's point. So what is 101? Point 101 is 0.625 in decimal, and so that's somewhere right around here. And so that actually encodes for the sequence 20, right? I mean, so we could have, if we didn't know that the length of that first thing was 4, then we might have made a mistake and said, oh, 101 is the first thing, and then decoded that immediately to 20, right? Because we would have said, oh, the first thing is a 2, and then the next thing is a 0. So that is the reason why it's not necessarily prefix code. In this particular example right here, 101 was a prefix of 1011, and that is a valid encoded message for this sequence right here, 20. So that demonstrates exactly right here that that the number version is not a prefix code. So that's because, so we just did an example. 101 is a prefix of 1011, and both are valid. Both are in the image of both are, I'll say it this way, both are valid under the number version. Valid encoded messages in the number version. So that's this first statement here. A is an example. A. And B, So the interval version, I'll just indicate without proving it exactly, the reason why the interval version is in fact the prefix code is that if, so I'll say it this way, if cx superscript 1 is a prefix of cx superscript 2, if the encoded message for some source sequence was a prefix of the encoded message for another source sequence, that binary sequence was a prefix of the other binary sequence, that would imply that x1 is actually a prefix. Under the interval version, x1 is a prefix of x2. So why is that the case? Well, first of all, supposing that this is true, I'll explain why that's true in a second. But if that were true, that can't happen, right? This cannot happen unless x1 equals x2, because if x1 is strictly a prefix of x2, then, this always ends in a 0, right? This ends in a 0, and so this would then have a 0 somewhere other than the last position, but that can't happen because we only are encoding messages. Only messages that we're considering are the ones that are valid with respect to our end of file condition. So assuming this is true, that proves B. I mean, I haven't formally gone through it, but you can think about it and see why that's the case. And the reason why this implication holds is, think about what happens here. Suppose this, so this is some binary sequence. Say this is, say just for illustration purposes, say that cx2 was the thing that we had here, 101, and say this here is a prefix of that 101 to be consistent with that. So let's go back up to our example. 10, here it is, example 1. This is the interval for 10110 right here. Maybe we can go over here and see it. 101100 is this guy. 101 is this guy, this chunk. And so whenever you have a binary sequence that's a prefix of another binary sequence, the chunk for that binary sequence contains the chunk for the other one. That's always true. So if 101 were a valid encoded sequence in the interval version, what does that mean? That means that there must have been some, some sequence, some original sequence for which 101, this chunk, was strictly contained in the corresponding interval from A to B. It wouldn't be this interval, because this is not contained in that interval. It would have to have been some larger interval, something like, something like this, that contains this 101 chunk. But then what would that mean? So maybe let me draw it here. So what would that mean? That would mean that that the sequence for the sequence of source symbols for the longer guy, for 101100, certainly would have the same sequence of source symbols leading up to that point. Because to get to that point, I mean, it wouldn't be on the left here. It would be like, wherever it would be like over here somewhere or something. Like maybe this one, not that one, maybe this one was like 20 or something. Well, you're subdividing over here, remember? So anything to the left, any other chunks to the left of this guy, are gonna be containing this guy, that chunk. And so the sequence that would lead you to this interval, to the smaller interval, up to this point is going to be exactly the same as the sequence that led you to the interval that contained this 101 guy. So that might have, hopefully that's clear. It might not be totally clear. You may have to think about that for a second if you want to really understand it. Think about why that's the case. But that's roughly the idea. The reason why, if this is a prefix of this, then this is a prefix of this. All right. All right. So that's why you might want to take this approach and make sure that the whole interval is contained in the interval from A to B. It's sort of a technical point, But if you really are interested in implementing the algorithm, then this is important. On the other hand, just for basic understanding of arithmetic coding, this is probably not an essential point to understand.